Okay, so we're busy discussing occupation number representation. Here is just one more example at the top here. So if I've got the state K1, K2, K3, K3, then the occupation number tells us we've got delta K, K1, delta K, K2, and 2 delta K, K3. So you see the occupation number function is summarizing for us which momentum states are filled with particles and how many particles are in each state. So this occupation number function is telling us there's one particle in the state with momentum K1, there's one particle in the state with momentum K2, and there are two particles in the state with momentum K3. So that's why it gets the name of the occupation number representation. I want you to notice something else as well, which is well worth noting, and it's the following. If you look at the formula that I've just boxed in red, our occupation number has a variable K appearing in it, but you might ask yourself, where does K appear in the state? And the answer is K doesn't appear inside the state, okay? So this K momentum for N is sort of like a dummy variable. It actually doesn't get translated into the state at all. So when I write the occupation number ket, I will usually write it as an N, and I won't indicate the argument. The argument of N of K is K. It doesn't appear when I write down the state, so I don't usually bother to write down what N of K is. The next thing that I would like to do is I would like to work out what is the overlap between two occupation number states. And the formula giving you that is this formula that I've outlined here in blue. So I'd like to prove this formula, okay? On the right-hand side, you can see that there's two ingredients. Well, there's a few things going on. First of all, notice that there's a product over momenta, product over K. Thank goodness we're working in a box where K is discrete. It makes it conceptually much more easy to think about what that product is. It's just this product over the discrete values that the momenta can take. So that makes sense. Then we've got N of K factorial. This N of K factorial we're going to see will be related again to boson statistics of our particles. And then we've got a delta function. The delta function is perhaps the most transparent piece of this formula. The delta function vanishes if n is not equal to n primed as a function. So the delta function makes sure that the two particles have the same, that the two states have the same number of particles in them, and furthermore, that the momenta of these particles match. So that's what the delta function's doing. Okay, I'm going to illustrate this formula to you by working out a few examples. So let's imagine that we had K1 and P1. So in this situation, if you were to read off what are the occupation number functions, we'd have a delta K, K1. So that's easy to do. What's the occupation number for N? Well, this would be a delta of K, P1. So if we plug it into the right-hand side of the formula, well, we'll take a product over all Ks, okay? So let's say that we're looking at K primed, which is not equal to K. That's one of the points in the product. In that case, the N of K primed is simply 0. It's 0 because K is not equal to, let me say this a bit better. Let's imagine that we're taking a momentum K, and K is not equal to either K1 or P1, okay? In that case, N of K is just 0 because K is not equal to P1. So that's just naught. we have to calculate n of k factorial, which is naught factorial, which is just a 1. Okay, so we'd get a 1. Similarly, for n primed of k factorial, we'd get naught factorial because k is not equal to k1, and that's 1. So whenever we're at a place where the occupation number vanishes, n of k prime is 0. If we look at what is delta n of k prime, well, it's delta naught naught. So that's a 1. So any states that are not occupied, the right-hand side just gives us a 1 in the product, and well, that's fine. That's what it gives us. Now, let's take a look at what happens this delta function becomes delta k1 p1. See, this delta function has to set delta of, oh, let me just kill this. It has to set delta of k1 equal to delta of k p1. So what is this equal to? Well, as you let k vary, sometimes the first delta will be 1 and the second will be naught. Sometimes the first will be naught, the second will be 1. That all gives you a delta of 0. The only time that your delta function could be non-zero is if when delta k1 is 1, then delta k p1 is 1. But that means k1 must be equal to p1. Okay. So this delta function just becomes k1, p1. All of the n factorials that we've seen sitting here, they are either naught factorials, or when we're at k1, they're just a 1 factorial, so that's just 1. So in the end of the day, this is what we'll end up getting. We simply get that delta of kp1 is equal to delta k1 p1, which is the correct answer, but I got it by evaluating the right-hand side of the occupation number representation. Let's try do another one. So let's take the vacuum naught naught, okay? If we've got the vacuum naught naught, then what is n of k equal to? Well, that's naught. What is n primed of k equal to? Well, that's naught. So if we take a product over k, n of k for any k vanishes, naught factorial is 1. So these n factorials just give us a bunch of 1s which are multiplied. And then we've got a delta naught naught. Well, that delta naught naught is indeed 1. So this is just equal to 1. Okay, great. I want to do one more example, which I hope is going to explain to you why that n factorial is sitting there. It'll just make it clear why it sits there. Okay, so let's do that now. And sorry, it's a bit of a tedious example, but I think that we do need to do it. So let's say that we have got the state K1, K2, K3, and we're going to work out the overlap with P1, P2, and P3. Okay, so let's see let's see what this inner product is. Okay, so think back to your old description of the Hilbert space. We had delta K1, delta K1, P1, K2, P2, K3, P3 plus. Then you remember, these states are invariant under swapping P1, P2, and P3. So we had to add in all of the states obtained by permuting. So let's do that, and let's try to not make any mistakes. But it is almost certain that we will make some mistakes. If you do catch a mistake, Sorry, guys, no prize. Let's see, 1, 2, 3, 4, 5. We need one more. Okay, so for the first one, let's swap 1 and 2. These should be P's. P, P3 stays the same. For the next one, let's swap 2 and 3. For the next one, let's swap 3 and 1. Now, we've got some funny swap of all of them. And again, some funny swap of. So those are the 6 terms. That's what our old inner product would have been. Good. So what will this become if we take K1, 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 P1, P1, P1? Well, then we should set all of the K's equal and all of the P's equal. And you can see that every single term just becomes a delta of K1, P1 times a delta of K1, P1 times a delta of K1, P1. Now, because these are Kronecker deltas, you know, if I take a product of 3 K1, P1s, that's just the same as having 1 K1, P1. So each term will just become delta of K1, P1. And there's 1, 2, 3, 4, 5, 6 terms, which, if you remember, is 3 factorial terms. So let's summarize this answer, because this answer I will want, and you've seen how I have derived it. Okay. This is 3 factorial delta K1, P1. Good. Okay. Now let's reproduce this formula from our occupation number representation. Let's see if we can do that. Okay. So now n primed of K, this is just 3 delta K, K1. N of K is just 3 delta K, P1 primed. Now, what is delta N of K, N primed of K, and let's take a product over K. Well, most of the time, N is naught, N primed is naught, and no problem, it's delta naught naught. In the specific case where K becomes K1, then N of K1 is 3, and N of K1 would also be 3 if K1 is equal to P1. So this product of all of your deltas, you know, what is it going to give you? It's just going to give you a delta K1, P1. When delta K1, when K1 is equal to P1, in that case, we know that the 2 occupation number representations are the same. So that we know. And what is the value of N of K? Well, the value of N of K everywhere is 0, but, so it'll be a whole lot of zeros, but at the point where K is equal to K1, N of K becomes 3. Now, the naught factorials are all 1s. The 3 factorial is just a 3 factorial. So our occupation number representation, after we've taken the product of all of the K's, indeed gives us a 3 factorial from this N of K factorial. But for most of the K's, it was just naught factorial, which is just a 1 in the product, which has disappeared. But for one special point, n of k was 3, and that gave us a 3 factorial. And then the two states are only the same if the state in the bra, which is a momentum k1 state, is the same as the state in the kit, which is a momentum p1 state. Okay, so please study this example. Please write down some more examples for yourself. At this stage, you should find it easy to translate between a state in Fock space and its occupation number representation, and you should find it easy to understand the formula outlined in blue, which is the overlap of two occupation number states.